Morning, everyone. How are we doing? Questions while we wait? We have class every day from now on. There are no more holidays. So, class every day until the end. Morning, everyone. I'm doing all right, thank you. Hope everybody's doing well as well. Questions while we wait? We're a bit early again. Well, you say minus 11, but I'm going to assume that it's minus 1. I'm going to assume it's minus 1. Right, so there it is. And what happens? Well, if you plug in x equal to 0, of course you recognize that this is 0 over 0. For the person asking about the quotient rule, yeah, if you're looking for the derivative of that quotient rule, it is. Right, so here 0 over 0, you know this is an indeterminate form, you know something's got to be done. What are we going to do? Well, what you have to realize is that if you consider if you define the function, if you look at the function tangent x, if you look at the function tangent x, and let me ask you this, what is the derivative of this function at pi over 4? Right, so first let's find the derivative of this function. You know the derivative is secant squared. And consequently, the derivative at pi over 4 is secant squared of pi over 4. Secant of pi over 4 is root 2. So this is just going to be 2. Right? What's the point here? Well, the point is that the derivative of the function at pi over 4, by definition, is the limit as h goes to 0 of f of pi over 4 plus h minus f of pi over 4 over h. And this is what? Well, here's our function. So that is tangent of pi over 4 plus h minus tangent of pi over 4 all over h. And as you know, tangent of pi over 4 is 1. So there you go. Now h is a dummy variable here, right? H is a dummy variable. So whether it's h or whether it's x, this is the same limit. But that is exactly what you had over here. So that is the derivative of the function at pi over 4, namely 2. How are we doing? It's a beautiful observation, right? How did we get the 2 at the end? We did it at the beginning. Tangent of pi over 4 is not equal to 2. Tangent of pi over 4 is equal to 1. People, what are we talking about? What's going on here? Seems to be lots of confusion about this question. It's tricky. But what you have to realize is that this is the definition of the derivative of tangent x evaluated at pi over 4. Again, I'm suggesting if you take a step back, look at this question and convince yourselves that it's the derivative of tangent x evaluated at pi over 4. Right? We have it here. The derivative of a function evaluated at pi over 4 is this. And if I take f to be this function, I get that, which is exactly what we have here. So our original question is disguised our function is really the definition, right? That's our original function. It's the definition of the derivative of this function evaluated at pi over 4. All right. Questions? Moving on. All right, let's do the implicit differentiation thing. And that will bring us back to where we were. So that's a good so find dy dx where you have this, right? So you have a you have y implicitly defined as a function of x, right? You shouldn't waste any time trying to isolate y equals a function of x. What you might want to do though, right, so I mean we're going to assume y is a function of x and differentiate both sides. You could do that immediately, or you know, I mean, since the left-hand side is a quotient, you know that in order to differentiate, you'd have to apply the quotient rule. You might want to bring the x plus y to the other side so that you don't have to apply the quotient rule. It's a personal choice. I think it's going to make it slightly easier. And you might, again, want to expand that. Again, you don't have to. It's really up to you. But if you do, xy squared plus x plus y cubed plus y, right? So this is what we have. I think it's going to be easier to work with this than the original, but you realize that they are equivalent. So if you differentiate the whole equation with respect to x, assuming y is a function of x, right? That's the whole principle behind implicit differentiation. You can go ahead and use the quotient rule, absolutely. The answer will be the same. So nothing wrong with that. But I think it's going to be a bit faster to do this. So let's differentiate. Derivative of x squared is 2x. Derivative of this is a product. So product rule applies. We differentiate the first one, leaving the second one fixed. Plus, we leave the first one fixed, differentiate the second one. Here you've got something squared. So the derivative is 2y. Then you differentiate the inside. Inside is y. The derivative of y with respect to x is exactly that, dy dx. Derivative of x is 1. Derivative of y cubed. Differentiate the cube. And then differentiate the inside. And finally, the derivative of y is just dy dx. And he's asking, can you write f prime instead of dy dx? Well, I mean, there's no f anywhere. So you better tell us what f actually is. So bring all the dy dx's to one side, everything else to the other. What do we have? 2xy dy dx. Right, I'm gonna leave these here and bring those to the other side. Plus 3y squared dy dx plus dy dx is equal to 2x minus y squared minus 1. Factor out and divide. So we see that dy dx is equal to 2x minus y squared minus 1 over 2xy plus 3y squared plus 1. And I claim, and I mean, I'm going to invite you to work it out, that this is exactly the answer you would have gotten if you had applied the quotient rule. Right, if you had left the answer as is, left the equation as it is, applied the quotient rule, you should get the same answer. All right. Where does that leave us, right? So, I mean, this is a nice throw back to Wednesday when we were looking at implicit differentiation. I'm sure you've practiced it. And now here's the question. Well, I mean, more than a question. Let's call it a theorem. Theorem. Let f of x be injective and differentiable. You could, of course, have used the product rule here instead of expanding. And again, the answers will coincide. Absolutely. Let f of x be injective and differentiable. Where am I going with this injective business? You know where this is headed. Where did we use the injective? In the inverse, precisely. Let f of x be injective and differentiable. Then f inverse is differentiable. And the derivative of f inverse is 1 over f primed of f inverse of x. Let's prove it. Because the proof is nice, easy. It's just an application of implicit differentiation. So this shows you the strength, the power of implicit differentiation. Proof. Well, first of all, we know, right? You know f prime, f inverse exists. Let y be f inverse of x. What do we want? We want the derivative of this, right? We want the derivative of f inverse. It's just a sum pump going off. You know that. So we want dy dx. So what are we going to do? Take f of both sides. You have y is f inverse of x. Take f of both sides. You do the same to both sides, equality is maintained. What is f of f inverse of x? What is the right-hand side? Right-hand side, thank you, Michael, is just x. All right, so what are we saying? We're saying that f of y is x. Now, let's differentiate this whole equation with respect to x. Assuming y is a function of x, which it is, right? Because that's really what we started out with. So implicitly differentiate this equation. Derivative of this, well, this is f prime of y times the derivative of the inside, dy dx. Derivative of x is just 1. So you see that dy dx is just 1 over f prime of y. But y is f inverse of x. So that's 1 over f prime of f inverse of x. Exactly the result. Very nice, easy. A simple application of implicit differentiation. How does the right side equal to x? Somebody want to address that? The f and f inverse cancel, exactly that. That's the definition of a function and its inverse. It's when the composition of the two cancel to give you x. In particular, if f of x is e to the x, what is the inverse? You tell me. Ln x it is. So the derivative of ln x, which is the derivative of f inverse, by definition, we just saw was 1 over f prime of f inverse. If f of x is e to the x, f prime, you know what it is. The derivative is just e to the x. So this is f prime, f inverse is ln x. So everywhere you see an x in f prime, you replace with ln x. This is 1 over e to the ln x, which is really, you see where this is headed. Exponentials and logarithms are inverse functions of each other. This is 1 over x. The derivative of ln x is 1 over x. So let's write that down. The derivative of ln x is 1 over x. And now the question arises naturally, what about any other logarithm? Good answer there, Jacob. What is the derivative of log base A in general? Well, we saw a change of base theorem. Log base A is the same as ln x over ln A. Right? This is just the change of base theorem. So instead of differentiating this, I can differentiate this. But ln A is just a constant. So this is 1 over ln A times the derivative of ln x. And the derivative of ln x is 1 over x. So that's 1 over x ln A. Very nice, right? Did Jacob mention that? I didn't see that. Yes, in fact, he did. So this is only for, right, because you know the logarithm is only defined for x bigger than 0. Let me point out, if we were to look at the derivative of ln of negative x, which here this would be defined for values less than 0, what is the derivative of ln of negative x? Well, this is by definition, right? I mean, it's just the chain rule. Derivative of ln is 1 over. So that's 1 over negative x times the derivative of the inside times negative 1. In other words, it's still 1 over x. Exactly right, Shumit. Still 1 over x. Conclusion, the derivative of ln of absolute value of x, right? Ln of absolute value of x is either going to be ln x when x is bigger than 0, or it's going to be ln of negative x when x is less than 0. Both derivatives agree. The derivative of ln of absolute value of x is 1 over x. And I'll let you repeat for the logarithm, but of course it's the same thing. The derivative of log base a of absolute value of x is 1 over x ln a. Of course, this agrees. When a is e, you get ln of absolute value of x here, and when a is e, ln of e is 1, so you're back to that. So let's keep those up. Ln of absolute value of x is 1 over x, well, the derivative, and the derivative of log base a of absolute value of x is 1 over x. And let's do a few examples from the book. Questions before we do so? I'm still getting questions about the midterm. We haven't written it yet. As soon as we write it, I'll let you know. But it makes no difference, right? I mean, you know the material, so and you know it's a 3-hour midterm, so it should take you 3 hours. You have 72 hours. So graphing this derivative, would it not only be positive? Would it not be only positive x? No, the derivative is valid everywhere except at 0. So we're good. As long as you stay away from 0, the graph of the derivative is defined. How we get 1, Mara, you're asking for 1 over x where? There are many 1 over x floating around here. We are asked to differentiate. The top part, this one here. Well, so we're differentiating this business. What is that? This is ln of something. The derivative of ln is 1 over. So 1 over this, and then you differentiate the inside as the chain rule, right? Chain rule is kicking in. So 1 over negative x times the derivative of the inside times negative 1. And then the negatives cancel, leaving you with a 1 over x. The material is all the way to the chain rule. I'll post the actual sections in the book that you're responsible for in an announcement on my courses. I'm a bit lazy here, right? For completeness, you should say for x not equal to 0, but we'll let it slide. As long as you know what the domain is, right? Because, I mean, we're not graphing these yet, but when we get to graphing, in fact, one of the questions that arises naturally is, what is the domain of the function? So it's not like you can forget all of it. It's going to be important. Consider this function. We're asking for the derivative. Differentiate. You know what to do, right? You recognize that you have a product here. So product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. Derivative of ln x is 1 over x. Derivative of x is 1. Here, this x over x is 1, as long as x is not 0, but x equal to 0 wouldn't even make sense here because of the line. And as suggested, you end up with ln x. You don't have to state x is not equal to 0. Again, we're not going to worry too much about that for now. Like I said, when we get to graphing, it'll be important to state the domain. But for now, let's concentrate on the differentiation. And there it is. You ask yourself, what are we looking at? And we've got ln of something. So the derivative of ln is 1 over. So 1 over sine squared times the derivative of the inside. But what is inside? What is inside? Inside is something squared. So the derivative of the square to sine times the derivative of the inside, right? It's chain rule over and over again. Derivative of the inside, derivative of sine is cosine. You can cancel one of the signs, and that leaves us with 2 cos over sine, or if you prefer, 2 cotangent. Exactly that. Let me point out that you could have simplified this question to begin with. By using properties of the logarithm, this allows you to bring the power down. So this is really 2 ln sine x. And the derivative of 2 ln sine x 2 is just a constant. We'll leave it out. Derivative of ln is 1 over. So 1 over sine times the derivative of the inside. Slightly simpler. A very nice observation. Of course, the answers agree, as you would expect. And this opens up the door to an important process known as logarithmic differentiation, which we'll see momentarily, but keep that in mind. Some people are asking how we move the 2 outside of the law. This is one of the properties of logarithms, right? Log of x to the r is r log x. Derivative of trig identities, perhaps you mean derivative of trig functions. And, here's the problem. I mean, this semester all the exams are open book, so memorize, don't memorize. Exactly. However, what I'm suggesting is you have to learn the material. Because who knows what's going to happen afterwards, right? I mean, this is this calculus, Cal 1, Cal 2 is the foundation of mathematics as we know it. And you use that stuff in your other courses afterwards. So you really need a good knowledge of calculus. And if you don't learn it now, when are you going to learn it? We're looking for the derivative. Derivative of log, right? That's 1 over secant x ln 10, right? That's what this says right here, times the derivative of the inside. What's inside? Inside is secant. Derivative of secant is secant 10. I cannot prove that immediately. That sine squared. Well, no, I mean, first of all, it's not sine squared. Well, Benjamin, I'm going to let you think about what you wrote down there. Because that's actually not an identity there. That's not true. How did we get the ln 10? Right. So Benjamin, that's the equality. How do we get the ln 10? Ln 10 comes from here. We showed that log base A as derivative 1 over x ln a. So in this case, ln is a is 10, and there you have it. So Benjamin, if you want to prove that, you will actually be able to prove it very soon with relative ease. Remind me when we do the mean value theorem. If you're still interested, when we do the mean value theorem, you'll have an easy proof that sine of 2x is 2 sine x cos x. Otherwise, the only other easy proof that I know would make use of complex numbers. And I mean, it's very interesting to realize that by moving to a more difficult setting, in other words, moving to the complex numbers, makes things much simpler. Let's do a few more. F of x ln of x over 1 minus x. I mean, it's the same question, right? We're looking for the derivative. And I'm sure you've recognized that what we're dealing with here is a quotient. So quotient rule applies. Vu prime minus uv prime all over v squared. While the derivative of logarithms will not be on the midterm, the more you know, the easier everything else becomes. So, I mean, look, it's not like it's difficult to remember that the derivative of ln x is 1 over x. And then what are you doing here? You're really practicing the quotient rule. So if you can do the quotient rule with ln x, you can do the quotient rule without ln x. And they're just as easy. Exactly that. Let's finish that up. 1 over x minus 1 plus ln x over 1 minus x all squared. Or if you want to bring the x down, I don't know that you do, but let's do it. We'll make it look better without having fractions in the numerator. you see the idea here, right? If you jump right away to differentiating, yeah, it's still raining. Still raining, not heavily, but it rained all night. So yeah, that's what you get. Right? If you jump right away to, seriously. The derivative of the logarithm is not on the midterm, that's correct. If you jump right away to differentiating this, what do you have there? You've got a log. So the derivative is going to be 1 over this. And then you have to differentiate the inside, right? Chain rule. And what's inside? Well, inside is a quotient. So quotient rule applies. And then when you differentiate this business, that's a product. So product rule applies. And when you differentiate this, it's going to be another chain rule. And you see that it's going to be a big mess. It's going to be very long and painful. Very easy for you to make a mistake somewhere. Instead of jumping right away to the derivative, we're going to be smart and we're going to say, well, the logarithm allows me to simplify this expression. You know that ln of a quotient is the difference of the logarithms. So already much simpler because you never have a quotient rule to worry about. Moreover, the log of a product is the sum of the logarithms. While I'm here, why don't I rewrite this as 2x minus 1 to the, you know what it is, 1/3. Thank you, Michael. And finally, ln of the power, we had it up there a while ago, you can bring the power down. So we can bring this 4 down. This is 4 ln x squared plus 1, and we can bring the 1/3 down. Understand now that we have not differentiated anything yet. This is still the original y. We have not applied the derivative. All we have done is simplify the function. Simplify the function so that it would be easier for us to differentiate. Where did the ln come from at the front? It was always there. This was the original question. So we have not applied any differentiation. This is still the original function. So now let's differentiate. And instead of differentiating this, we're going to differentiate this, which is an equivalent reformulation. Derivative of ln x, 1 over x. Derivative of this, the force constant. Derivative of ln of this, so 1 over, times the derivative of the inside. Still a chain rule, but a chain rule so easy that you can do it just by looking. And finally, minus 1/3, derivative of ln is 1 over. times the derivative of the inside. There it is. Trivial. Trivial because you took the time to simplify the expression. I'll invite you to try to differentiate this without simplifying it. Right? Derivative of ln is 1 over, so you get 1 over this. And then you have to differentiate this business. That's going to be a lot of work. How are we doing? Exactly. Trivial compared to the alternative. The 2x comes from the x squared plus 1, exactly, right? It's the derivative of x squared plus 1. There it is. You could apply properties of logarithms again. Maybe you, why don't we do that? The log of a product is the sum of the logarithms seems like the thing to do. Web work usually doesn't care if you simplify or not. Usually. So the derivative of log base 2 is 1 over x ln 2. Derivative of log base 2 is 1 over x, or 1 over u, ln 2, times the derivative of the inside, times du dx. What's inside? A log base 5, whose derivative is 1 over x ln 5, and that's it. Why isn't there 1 more plus x? Where are we talking about? On the midterm, I will tell you if I want you to simplify or not. Well, I'm rubbing it off now, perhaps a bit too quickly, but I wanted to bring your attention to the fact that we use properties of logarithm to simplify the expression originally. And I suggested that this was very useful in what is known as logarithmic differentiation, which we'll consider right now. But we have that idea here a bit, right? Instead of differentiating this thing originally, we broke it up into simpler pieces. How do we get this? The derivative of log base 2, let's call this u, right? So it's log base 2 of u. The derivative, d by dx of this, is 1 over u ln 2 times du dx. That's what the chain rule says. And this 1 over u ln 2 coming from right here, where u is this business. Consider this. Consider this question. Again, same question as always, find the derivative. Well, you're thinking to yourself, we have three functions multiplied together. So, you're going to differentiate the first one, leaving the other two fixed, plus leave the first two fixed, differentiate the first and third one fixed, differentiate. Anyways, you know the deal. You know how to do that. It's not so bad. But if you had a logarithm there, you could make use of the logarithm to simplify things first. But you don't. Right, the question is find dy dx, where y is this? You don't have a logarithm. But if you did, you could simplify first. But you don't. So take it. If you do the same to both sides, equality is maintained. Take the logarithm of both sides. Nothing wrong with that. And if you do that, now the right-hand side can be simplified. Right? Now the right-hand side, log of a product is the sum of the logarithms and again, ln of a power, you can bring the power down. Here the logarithm and the exponential cancel. And this is still ln y. We haven't differentiated anything yet. Well, it's a nice, useful tool, taking the log. So ln of y is equal to that. But what do we want? We want dy dx. So differentiate the whole equation with respect to x. Assuming y is a function of x, which it is, right? We have it right here. So differentiate with respect to x, what happens? Differentiate both sides with respect to x. What is the derivative of the left? Derivative of ln is 1 over, right? So it's implicit differentiation. 1 over y times the derivative of the inside times dy dx. Derivative of the right-hand side? Well, that's easy. 1 over 2x. 2x minus 1. And 2 over 3 times x plus 1. Bring the y to the other side. And there you have it. Except, normally this would be fine in an implicit differentiation setting. But you know what y is. Y is already this. So root x, e to the x squared minus x plus 1 to the 2/3 times this whole thing. If you can express the derivative as a function of x only, then of course it's very desirable to do that. isn't it root of x instead of x for the first one? And as Michael suggests, the answer is no. Root of x is really x to the 1/2, and I'm bringing the 1/2 down. So that's the idea behind logarithmic differentiation. You take the logarithm to simplify the expression. Very nice. All right, we take the logarithm to simplify the expression, make it much easier to differentiate, and thereby removing the possibility of error. The last step, all I'm doing in the last step is I'm replacing y with what it was. Making the whole derivative a function of x only. Well, that's the thing, right? You can use these strategies now on the midterm. Even though the logarithm, even though you don't need the logarithm on the midterm. We've seen it in class, so you can use it. Don't read too much into that. Some of you may be familiar with L'Hopital's rule, and now may want to use L'Hopital's rule on the midterm. The answer is no. If you use L'Hopital's rule on the midterm, you'll get 0 for that question. And the reason for that is very simple. We're testing you on the other techniques. Well, exactly. If you don't know L'Hopital's, forget about it. But if you do know it, you're not allowed to use it on the midterm. Now consider this. Y equals x to the 1 over x. Yeah. I know, Matthew, you weren't asking specifically about L'Hopital's rule, but rather the idea of logarithmic differentiation, perhaps. And I'm going to encourage you to use logarithmic differentiation on the midterm if it applies. That's not an issue. I just don't want people to read too much into that and then start using techniques which we have not seen. So if we've seen it in class, you can use it, even if it came in material after. But if we haven't gone there, in particular, L'Hopital's rule, please stay away from it. It's not that it's bad. L'Hopital's rule is a very powerful tool. But it's a tool that once people know L'Hopital's, they tend to forget everything else. And I don't want that to happen. All right, Benjamin, so this is a different question then. Right now you've thrown in the derivative, and that is correct. And why is it correct? It's because what you're looking at is sine x squared. So if we differentiate that, you've got something squared, we differentiate the square. So you get 2 sine x to the 1. And then you differentiate the inside, the derivative of sine is cos. That's why. Consider this. Consider this x to the 1 over x. You see what's happening, right? This is really a combination of two things, right? It's like an x cubed, and it's like a 2 to the x. It's the two things put together. We don't have a rule for the derivative of this function, but it doesn't matter. We can still find the derivative by doing logarithmic differentiation. Take log of both sides. This allows you to bring the 1 over x down. And now you don't have this issue. You don't have this issue of a function of x that is raised to a power of x. Right? Ln of y is now just ln x over x. So you can differentiate the whole equation with respect to x without any difficulty now. Derivative of ln is 1 over times the derivative of the inside. Derivative of this, quotient, so quotient rule applies, vu prime minus u v prime over v squared. So this is 1 minus ln x over x squared. Bring the y to the other side, and you're done. You can do the product rule. You can do the product rule, viewing it as 1 over x times ln x. Either way, nothing wrong with that. It'll give you the same answer in the end. What are we saying? dy dx is therefore y times this. And y is x to the 1 over x. How are we doing? We're back. Excellent. Thank you. So there it is. Again, question is, what, not back? Some people are back. I'm not sure what you mean by a never-ending process. If you just keep taking the derivative. You mean like a second derivative here? If you differentiated this business? With the product rule, you got, what is the derivative of this? The derivative of this is minus 1 over x squared, right? Matthew? Maybe that's where you're missing the negative. Well, I mean, so the point is, if you differentiate this again, I mean, you know, it's going to be a product rule with the derivative of this happening, and so on and so on. All right. Same question, we're looking for the derivative dy dx. And, right, again, we have a function of x to a power, which is a function of x as well. Well, that's the important thing, right? Making a Taylor series with these kinds of functions. That's the nice thing we want to aspire to. So we're looking for the derivative. Let's take ln of both sides, which will allow us, well, right, I mean, can this be a chain rule? The thing is, we don't have a formula for a function of x raised to a power, which is also a function of x, right? That's what I was suggesting here. It's kind of a mix between these two things. It's almost like a power of x, but almost like an exponential as well. It's really a mixture of the two. Never mind the Taylor series reference there. We'll see that at the end of 141. It's beautiful stuff. So taking ln allows you to bring the power down. And rewrite it this way. Well, but that's the thing, you cannot just take the exponent down. What do you mean by that? You mean just bring the ln down here? That, I mean, does anything work like that? It doesn't. You know it doesn't, right? I mean, it's not like x cubed is the same as 3x. You cannot just take the exponent down. These are two different functions. But now that we have this for the chain rule, so you're really thinking, so I mean, if you do that, then you're really just treating it as an x cubed. Right? If you think that the derivative of this, I'll bring the ln x down and I'll subtract one from the ln x and then I'll differentiate the inside, then what you're really doing is you're treating it just as an x cubed kind of deal. You're treating ln x as if it was a constant. But it isn't. It's also a function of x. So you cannot do that. Differentiate the whole equation with respect to x, assuming y is a function of x. What do we get? Derivative of. Why doesn't that work? Well, it doesn't work because this is not a constant. You're treating it as if it was a constant, but it's not. And you're neglecting the fact that it kind of looks like this as well. So if you got it now, and I'm sure you did, I'll show you something in a moment. Let's take the derivative here. What do we get? Derivative of ln is 1 over. So 1 over y times the derivative of the inside. And what is the derivative of this? Here we have a product. So product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Derivative of ln is 1 over times the derivative of the inside. Benjamin's asking a good question, and let's hold off on that. I'm going to address that in a moment. Bring the y to the other side. And y was originally sine x to the ln x. Which is this. Normally that's it, we're good. This is the answer we're looking for, and let's leave it as that. But to answer Benjamin and Maxwell's questions, let's expand just to see what happens. Multiply that in. So this is how do I want to do that now? Let me write it like this. This plus this times that. I've got a sine x here. So let me cancel out a sine x with this sine x. So I'll have a sine x to the ln of x minus 1. And there we have it. What do I want to achieve here? I want to point out that this was both, right, something that looked a power of x, right, this to a power, but also an exponential. So it was a mixture of the two. If you treated this as just a power of x, the derivative would have been what? You would have brought the power down, sine x to the ln x minus 1, and then you would have differentiated the inside. Chain rule, right? But if you treat it as an exponential, something to the power ln x, then the derivative would have been a to the x, so sine x to the ln x, ln a, times the derivative of the inside. Yeah. So you see that this is actually the sum of the two things. Right? This thing is right here, treating it as a power. And this thing is right here, treating it as an exponential. Isn't that amazing? That really is amazing stuff. Exactly what you would expect. Is there a general rule? Well, it's an excellent question. And now I'm going to invite you to come up with your general rule. You're asking yourself, if I have a function that is raised to another function, what is the derivative? So find the derivative of this using logarithmic differentiation. You should not do this one. Logarithmic differentiation is the method of choice here. But if you want to come up with your own rule, now that you should memorize that rule or use it in any way, but it's a nice exercise to come up with your own rule for a function of x raised to a power, which is another function of x. You're going to do that using logarithmic differentiation. You're going to say y is f of x to the g of x. Take the ln of both sides and work out what dy dx is. Exactly that. Well, logarithmic differentiation is the process of taking the ln of both sides first and simplifying before differentiating. Seems complicated when you first encounter the name logarithmic differentiation, but you recognize that there's nothing there. How are we doing here? Questions? Perhaps a good place to end then. Unless there are any questions? Indeed. So, thank you all for coming. You guys have a good weekend. I will post on my courses the list of sections from the book. If I forget, if I haven't done that by tonight, somebody please remind me. But I hope to do that before 8 o'clock tonight. So thank you all for coming, and you guys have a good weekend. I will see you on Monday.